All right, hello YouTube. You can say hello as well. All right, that's very enthusiastic. Nice hustle. By the way, if you ever find me in a shitty mood but need something from me, you just have to bring me a cup of coffee and I'll basically do anything. Yeah. Black. Black like my soul. No sugar.
You're going to get 6 coffees before the midterm.
I better get 6 coffees before the midterm. I usually say to my classes that my other class brings me coffee, but you're my only class, so that trick's not going to work this time. Plus, I shouldn't reveal all my secrets to the internet, but... So there's a camera right there at the back of the room, too. I don't know if you all know this, that like a lot of these lecture halls have like security cameras, and they won't give me the footage. There's a camera right there that's pointing at both boards. You tell me why. I know why, because they want me to pay $50 per class to have the lecture recorded. And if they give me this, then I can do it for free. But you should be pissed. You should demand that the university records all your lectures. You pay like an extraordinary amount of money for these things, right? So, god damn it, they should be recorded. When I was teaching in Australia, everything was recorded. You had to opt out of the recording. You had to give a good explanation as to why you didn't want to be recorded. So, you guys should pick it or something. I don't know. Okay, so let's start today. It's going to be a short lecture because this is just trig and I hate it. And you probably hate trig too, but you have to love it. And then afterwards we're going to go and do a worksheet probably in the second half of this. So let's just see how far we get today. The topic at hand is trigonometry. Trigonometry. Okay, so trigonometry is basically the study of triangles. Why do we care about triangles? Anyone have any idea? Well, physics really cares about triangles because often when you set up related rates problems, which we'll be doing later in the year, these relates problems usually just end up relating rates along different sides of a triangle. But anyways, I'm going to tell you a bunch of stuff that you should know already. We have this thing called radians, and pi radians is equal to 180 degrees. So in this class, we never use degrees unless we're very explicit about it. So if you ever want to write a degree, you be sure to write that degree symbol there. Otherwise, we're just going to be using radians, and we will not be writing this. So it is assumed if we're doing an angle, that this angle is going to be expressed in radians. Okay, so, is this correct? Yes. What angle is this in radians? What angle is this in degrees? 90. So if pi radians is 180 degrees, half pi over 2 radians. It's got to get you guys to exercise a bit this morning. Okay, what about this? If I take this line, what is this angle? Pi. If I cut this, or bisect this, into equal parts, what's this? Yep. How do you know that? Because it's the whole thing is pi. I cut it into 3 pieces. What remains is pi thirds. What's this piece here? Also pi over pi thirds. Okay. What about this one? Two pi thirds, right? Because it's pi thirds here and another pi thirds. That's 2 pi thirds. So this should just be a reminder from high school. All right. There's something that we have. It's a little bit of a nuance that you guys are going to have to get used to. We have something called standard position. That is to say, the real axis, or real plane, is broken up into quadrants. Which one is the first quadrant? Yeah? First quadrant, second quadrant, third quadrant, fourth quadrant. this is weird in two ways, because we're starting here and we're counting anti-clockwise. The reason I'm telling you this is because we define angles like this. This is a positive angle, right? Positive. And this is a negative angle. So when you're working on the real plane, you got this angle. You got to remember that you have to treat it as negative. Right? And so this is because when we're taking lengths to sides, so my screen went black, so hopefully that indicates everything is working perfectly. There's a green dot, which means it's spying on me. Just be careful that so if we have positive degrees, you go this way, and radians. Positive radians, you go this way. Negative radians, you go this way. So just be careful about which way you're moving for what. Where's Dr. Cook? Here. This is what I use when you guys start talking too much. I'm only half joking. It's actually for this. Don't ever let me use this board. Okay. Anyone tell me what the definition is of a similar triangle? Yes, sir.
It's, say, two triangles that have different lengths with the same angles.
They don't necessarily have to have different lengths. The two identical triangles are similar.
But they have to have the same angles.
Yes, so don't include the second condition. Yeah, so two triangles are similar. Two triangles are similar when they share two would have given me all interior angles. So what is special about similar triangles? What's special about triangles in general? Why did we teach you about trig? Yeah.
They're maintaining the same angles and the ratio of the lengths of each side.
Perfect. The ratios among sides of similar triangles are equal, which is pretty amazing. The Greeks figured that out. So what I'm trying to express here is this. Here's an example. So I give you this triangle, and it has angle theta, and this is 90 degrees. And let me call this little h, little o, little a. And then I give you this triangle. Whoops. We call this big A, big O, big H. Okay. So if I have two triangles like this, and this is a 90-degree angle, and this is theta, and they're indeed the same angle, if you came up to the board and measured this with a ruler, the sides, if you measured this and divided by this, you would get the same thing as this divided by this. Right? So generally speaking, you have things like little o over little h is equal to big O over big H. Little a over little h is equal to big A over big H. What's the last one? O over A is equal to big O over big A. Which is kind of cool. Right? Why should the ratios of triangles that are similar be equal? But that's basically the starting point of all of trigonometry. This is the boring part. I need to get a bigger brush. Okay, so because similar triangles have this property, it is handy to have notation for the various ratios. Because if two similar triangles share the same ratios among their sides, all I really care about is the ratio among the sides, those things that I wrote up there. So in mathematics, when you start writing something over and over and over again, it becomes useful to introduce some notation or shorthand. So, if I give you this, so here's that same triangle I wrote up there. Here's a right angle. So we have to name the sides now, and this is how we name it. So I'll give you the easy guy. What is this called? You don't have to whisper the answer when it's right. Hypotenuse. This is called O because it is opposite of this angle. And this is called the adjacent because it's the last one. So that's how I remember it. I remember that this is the hypotenuse, that's the free one. I remember that the opposite has to be the opposite of the angle, and that the adjacent is the thing that's remaining. I have no good way of remembering that guy. Okay, so let's write down all the ratios of sides that we get here again. So you get O over H, O over A, O over A, over H. Ba, 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 ba. A over H, O over A, and then you get all the reciprocals of these. H over O, H over A over O. Okay, so let's give these names. What should we name this? Of what? Right, so it's important to tell me what the angle is, because if this theta was here, then I'd have to relabel all of the things. Okay, so the notation, because we use these all the time, these ratios. So let's just call this ratio sine theta. Let's call this ratio cos theta. Let's call this ratio tan theta. Like, we didn't invent these pieces of notation to torture you guys. We invented them because they're used so often that it's meaningful then to introduce things like these. So I don't have to say, oh, this is O of an H of this triangle with this angle. Right? All of that information is now encoded into this function. Okay, so what about the reciprocals? What is this guy? I think it's cosecant theta. This one is secant theta. And this one should be cotangent theta. Okay, so I'll tell you how I remember these. Cotangent is obviously the one that's the reciprocal of tangent. I remember secant goes from cos because there's a c at the end of here and a c that begins here. And then this is the stupid one that is the leftover. Right? Just like the adjacent. I think I'll probably give you this as a... I haven't actually thought about this yet. Would you guys want a cheat sheet for your midterm? That you prepare or that we prepare? See, if you prepare it, it always ends up being silly. I see people bring in magnifying glasses. They think they're going to write down the solution to every possible problem of calculus before the midterm. Okay, so why don't you go ahead and prepare a cheat sheet, and maybe I'll let you bring it. But I'll definitely prepare something, and maybe I'll include these triangles. All right. Oh, by the way, I've already scanned these and put them on Piazza for you, so you can always just pay attention when I'm lecturing. Because it's hard, and I put effort into it, and I appreciate the attention. But you don't have to copy. It's already online. So what's better? You like the board ones better, or you like the slides so far? Yeah, I like the board better too. So let's hope that, because it's for one, a hell of a lot easier for me to prepare handwritten notes than it is these digital ones. So if this works, then I'll continue doing board slides. Board presentation. Yeah, I don't know. Okay, so now we have to talk about circles. So I'm going to draw a circle, and hopefully it's going to look like one. Ready? Just got to do it fast. That happens a lot because the chalk that they give us is terrible. Let's try again. So so you always draw your circle first, and then go ahead and draw the axis. If you do it in the opposite order, you'll never get a nice circle. So here's the circle-ish. Let's pretend the circle has radius 1. So this is a 1 here. Okay, so I told you about similar triangles, right? So if triangles have the same angles, they have all the same ratios, those quantities I put up on the board. So what we do in math is basically say, well, if all these triangles that are similar are essentially equivalent, let's pick one of them to be the representation for the whole category of those triangles. So what we're going to do is just assume that every triangle we work with has a hypotenuse equal to 1. That's a way for us to standardize. So the standard triangle is the one with a unit hypotenuse. And if you have a unit hypotenuse, every triangle with unit, you guys know what I mean when I say unit, yeah? Unit 1. Okay, maybe I'll write that down. Unit equals 1. And I guess a G unit would be G. It's a wrapper? Oh my god. One day I'll make a reference that hits. I usually just shit on Drake. Okay, there we go. God's plan. All right. So if I write a triangle in here, and this triangle has this angle, and this is right, so what's the hypotenuse here? 1, right? Because it's inscribed in the interior of a unit circle. So what does this mean? Or how does this simplify our equations up there? Let's just look at the sine and cos. So if the hypotenuse is 1, this means that sine of theta is O opposite, and cos of theta is just A, the adjacent. But what are these here? So if this is O, so the opposite angle is this. So I'm just going to erase this part of the circle and this part of the circle. So I can do this. The length of this is what? Yes, miss? That is true, but what value from the board is it? What is this side of the triangle? It's the opposite. Is that this? Yes. So this side is equal to sine theta. Yeah? What about this guy? It's the adjacent over the hypotenuse, which is 1. So in this case, this is cos theta. What does that mean? What does that mean about this point here? What is it? I like these lulls. It gives me a chance to drink some coffee. But where's that point exist on the plane, right? You need two components for the point, the x component and the y component. What are the x and y components of that point? Yes, sir. Of what? And in what order? Cos itself is a function. You need to tell me what it's a function of. One is wrong, the other one is correct. So this point P here is cos theta, sine theta. Right, so what does that tell us about the graph of the unit circle? Can you generate the points of the unit circle now? I told you what all the points were. So can you collect them into a set for me? This is going to be cos theta, sine theta, the point, such that theta is goes from 0 to 2 pi, exclusive. Right? So if you run theta through this interval, you're going to generate a bunch of points, and all the points that you generate are going to be the ones that end up on the unit circle. Isn't that interesting? I think it's interesting. Okay, what's the other thing that we've discovered here? If the hypotenuse here is 1, and this is cos, and this is sine, what's the relationship between those three values? It's called Pythagoras' theorem. I'm positive you've seen it before. Yes, miss? Cosine squared theta plus sine squared theta is equal to 1 squared, but I'm just going to leave it out. Now you know where this comes from. It comes from here. Right? Rah! More cool stuff to come. Oh, they took the rope. Thing is the bane of my existence. Oh. All right. Okay, so we're going to reflect a bit. We just derived this. Sine squared theta plus cos squared theta is equal to 1. What other equations do you get? What other equations do you obtain from this? Any ideas? All of these trig formulas showed up. They're just simple derivations from equations. So can we get any other expressions from that expression? Yes, sir. I'm looking for a more significant type of change than just moving something to the other side of the equal. So I'm going to name this star. What happens if I take star and divide it by sine squared theta? What happens? Well, what's sine squared theta divided by sine squared theta? 1. That's the easy one. What's next? What's cos? Okay, great. Tan what?
Tan squared theta.
Tan squared theta. And finally, this is equal to what?
Secant squared theta.
Cosecant squared theta.
Oh, cosecant.
Okay, also note that when I write sine squared theta, that this means sine theta squared. We also have a different notation for the inverse of sine that I'll talk about when we get to inverse. Okay, so that's one thing that we've done. What's another thing that we can do? Yeah, exactly. This is star divided by cos squared theta. So what do you get now? I'll do the easy one. Plus 1. Well, what's sine squared theta divided by cos squared theta? Yes, miss? Did I do the first one wrong? Oh, yes. Shame on the rest of you for allowing that mistake to go by. So, by the way, this was a deliberate error. I was just trying to see if you guys were keeping up. So, You may assume that all my errors from now on are deliberate. Okay, so back to, then what is sine squared divided by cos squared theta? Okay, now it's the tan theta. Squared theta plus this, and then what's on the equal side? Should be 1 over cos squared, yeah? Which is what? Secant? Is it secant? Okay. Alright, so there are two other deductions that you can get. So these things don't appear out of thin air. They just are the way they are. I wish one of you were an engineer, because I want you to design a blackboard that erases itself when I pull it down. That would be amazing. All right. Okay, we have to be careful when taking signs. Oh, I seem to have skipped something. So you're going to have to help me reconstruct something. I'm very rarely going to tell you to memorize something, but occasionally I will. So here's what I want you to memorize. I want you to memorize these two special triangles. The first triangle is 1, 1, root 2. That's a right angle. What's the degree here?
45.
Or radians?
45.
Huh? Pi.
Over
I'm hearing a lot of guesses. 17. This isn't the Price is Right, people.
pi.
Yeah. $1, Bob. Pi over 4? Okay, let's work this out then. What's the sum of the interior of a triangle? 180 degrees, okay? So the last time we're going to say degrees. I'm going to get so triggered. So the sum is pi. The interior sum of the angles of the triangle is pi. What's this angle? Pi half. So the remaining two angles have to be half of pi half, just pi quarter, which is what you said. But that's how you'd work it out and be certain about it. This is pi quarter, this is pi quarter. Okay? So this triangle now allows you to recover the sort of cos, sine, tan values, right? So for instance, cos would be what? Opposite. I honestly forget these ones. Tan is easy, 1 over 1. Sine is opposite over adjacent, so that'd be 1 over root 2. So that's why this triangle is useful. The other triangle, which you're going to have to help me with because I legit forget. It's the one with pi third and pi over 6, right? So pi over third and pi. So this is 3. No, it's not. It's 2 pi 6 plus, yeah, so that's 90. Help me label the corners now. This is what? 2? You think so? Can I ask someone who's short? Yes. It's 2. The adjacent? 1.
Root 3. Root 3.
Okay, so I can rely on you guys to memorize stuff, it would seem. Which is good. Memorize these. Seems you already have. Okay, here's an example. So you have to be careful with signs when you're working these things out. What I mean by this is if I give you a angle, and this is pi over 3, okay? You have the pi over 3 triangle, so opposite pi over 3 should be root 3. This should be 1, and this is 2. So what's special now about this problem? If I ask you for cos of, well, this isn't pi third, right? Well, this is pi third, but what you're actually taking is the cos of that angle, 2 pi third, right? So to get the cos and sine and tan of 2 pi thirds, you can use the pi over 3 triangle, you just have to make an adjustment. What's the adjustment? What gets minus?
Oh, do we just subtract to find beta?
That's it. Because you're in the negative part of this, right? So you just, if you're here, like this has to be negative, like you're at -1 on the x-axis. Same is true if this goes down, right? Then you'd have two negative angles. That's all you have to do to remember. It's like how to get the right, like just draw your triangle and then label the sides that are in negative regions appropriately. And then all the signage will work out. This is how I remember it. There's also another, I think there's like a cast rule or something like that. I don't really like it. Right, because I told you exactly what the points here are. I told you that every point, I told you that every point here should be cos theta sine theta. And just be careful that the theta that we're talking about is this one. Right, so if I ask you to get the angle, to get me the ratios here, which of cos and sine is going to be negative? Cos is going to be negative, because look, wait, no, cos will be positive. Cos will be positive, right, because this is positive x. This is negative y, so in here this sign, in order for this to be the point here, this has to be positive, this has to be negative. That's all you can remember. Once one of these fell on me. Yeah, it was not very fun. But from that experience, I learned that one of my students, a good student of mine, thought Canada was in Europe. I'm serious. He's like, well, that explains your accent. I'm like, have you never seen a map? Okay. I have all of these tiny bits of sad-looking chalk now. Okay, two pieces of notation which is going to help me write faster on the board, so don't freak out. Personally, when I was in university, I loved getting these two pieces of notation. They made me feel like a genius. Anyways, we have this funny backwards-looking E and this funny upside-down A. This is just, I'm going to write these, and they're going to just be stand-ins for the following phrases. Backwards E is there is, or there exists. Upside-down A means for every. Right, so exists, E for every, slash for all A. And so you can use these in all your classes. It's a short form. Okay, so I'm going to write something. I'm going to write down the definition of periodicity, or what it means to be periodic. And I'll show you how we have notation now that allows me to really express things compactly. So let F be this. So when I write this, what is F? What does it mean when I write this? No. We did it yesterday, yeah. F is a mapping, which takes real numbers to real numbers. That's what that says. I'm going to add this. What does that tell us now? Well, that the mapping itself passes the vertical line test. Right? So that when I write let f from R to R be a function, what I'm trying to say is that we have mapping that's legitimate, like that passes the vertical line test, so we can use it as a function. Can anyone tell me what it means to be periodic? Can anyone give me an example of a function which is periodic? Mm-hmm. Sine, cos, tan. But why is it periodic? Repeats. That's a good place to start. Can you give me an algebraic expression that says this function is repeating? What property does the function have that makes it repeat? How can you encodify that in mathematics? Encodify, I just made up a new word. Codify or encode. Yes, sir. The same values are repeating after a certain point. Which values, which point? It's a good. We have to be much more specific, but it's good. We're heading in the right direction.
Like set an integral like 2 pi, where like the function starts and ends, like from 0 to 2 pi, and then
Well, periodic functions go on forever, so it doesn't start and end. You must be talking about one period of that function.
1 period, and then you basically just multiply it by n, which is like
You have to give me an expression. That means that you have to say something like, this function is periodic when? Statement. So function is periodic when there is a p called the period in R, it's a real number, such that f of x plus p is equal to f of x for every x in the domain of f. Like let's think about this for a bit. So here's a periodic function sine. Cos. Why not? It's a long forgotten brother. So what's true about this is if I write a line through here, that this point can be found again. Oh boy. It would be this one. So here would be p. Okay? So here's an x, and f of x plus p is the same one. F of x plus p is the same guy. And that's true for every line. Right? So if you take this guy, you should find the same point p units down. Okay? So you guys gave me the English. Close enough. This is the algebra. This is the geometry. But we need to start getting better at being able to write stuff like this. Because if I ask you to do something on a midterm, and you write me a fairy tale, when all I want is this, I can't give you too many marks. Any questions so far? Okay. I'm going to show you something fun about those. Oh, that is a great sound. What time is it?
11:50.
Thank you. Okay, so just recall this. Recall that I told you that all of the points here, P, are cos theta, sine theta. And I'm just going to write this now. I'm going to write this, instead of being the adjacent, I'm going to write x. And for this, I'm going to write y. Because that's basically what this is telling us. The x and y coordinates. Now, I'm going to tell you a couple things. So if you remember this triangle, circle, this is a circle, this is a triangle. If you remember the unit circle, and that the unit circle has these points on its graph, you can reconstruct that picture, even if you totally forget it. Why? I'm going to tell you what cos and theta can be regarded as. So cos of theta can be regarded as how far P is from what? So cos of theta is x, which is this. So what am I measuring? What is this x distance for P? It's this distance, right? So this distance here is the same as this distance here. And this distance is what? The distance from P to the, I heard it, I catalog everyone who answers properly in class and give them extra marks in the final. Well, this is the y-intercept, but, well, not really. This is the y-axis. So this is the distance to the y-axis. Right, so how far p is from the y-axis? Okay, and sine theta, I think this is cool. How far p is from the x-axis. Okay, so let's see how much of these plots we can reconstruct then. So let's just do 1 pi, 2 pi. And let's do here pi, 2 pi. Okay. So let's find zeros first. Why did I do it like this? Okay. Okay. So given that I'm telling you cos theta is how far p is from the y-axis, for what angles is cos theta 0 away from the y-axis? So track this point. Well, we can start here at 0. Right, so here's angle 0. This is a unit circle. This is p when theta is 0. How far is it from the x-axis or y-axis? 1. Everyone get that? The distance from here to here is 1. So for cos at 0, the distance to the y-axis is 1. So we at least have the point 0, 1. When is p 0 units away from the y-axis? For what angle? Well, we're getting closer and closer and closer to the x-axis as I move p, until I hit what? Here. How far am I from the y-axis here? Huh? This is the y-axis. So if I'm here, how far I am from it? 0. Right? So at pi half, I should be at 0. I keep moving this p. Now I'm getting further and further away from the y-axis until I hit this point. At this point, how far I am from the y-axis? Okay, the magnitude is 1, but since we're on the real plane, we have to report that as -1, because that's where we are, -1. So here, I should have drawn bigger symbols. Here we're going to be at, we're going to have this point. It's going to be pi -1. And then the point keeps on spinning around until it hits here, in which case it is 0 away from the x-axis again, y-axis again. So that means I'm going to be at 0 at 3 pi half. And then I move all the way back, and at which point I am again 1 away. Okay? So I start far away. I'm getting closer, getting closer. I'm on it. Okay, my arms aren't long enough. Then we're getting farther and farther and farther, and then closer and closer and closer, and then like this. Yeah, it is cool, eh? Okay, so you thank you. We can end class today. That's all I wanted. But these things are all related to one another. That's how the circle is related to these funny curves. All right, the physicists have more fun type of things because they bring in springs and stuff like that. They always have great toys. But in any case, let's just do the 3 points here. Okay, so sine theta is how far p is from the x-axis. So when I'm here, how far am I from the x-axis? When I'm here, how far I am from the x-axis? 1. 0, 1. Okay, start at 0, we hit 1, then we get farther away, then we get close again, then farther away and both. Okay? That's how you can see, that's the relationship between these loops and this unit circle. Okay? So you've got to commit really this. All you got to do is remember this. And you can get everything else from it. Right? That the points on the unit circle is cos theta, sine theta. By the way, I hope you see now how we go from here to getting x squared plus y squared is equal to 1 being the equation for this. It's all related. Cool. Sort of begs the question, though, why no one's ever told you that before. Math is interesting. I know it doesn't feel like it. I know it feels like we invented calculus to torture you. It's only partly true. Oh, no more chalk. That's fantastic. All right. So I'm just going to give you a bunch of equations that you're going to have to remember, but maybe I'll just give them to you. So remind me about that. Additional identities. Okay. So we're going to do trig now, and we're not going to use it for a bit, but then we're going to start integrating, and we're going to use it a lot. All right, so you're going to have to get sort of comfortable with these angle formulas. So here's the first one. Cos A plus B is. Anyone remember? I don't remember though. Okay, so cos A plus B is cos A, cos B minus sine A, sine B. Sine A plus B is sine A cos B plus cos A sine B. These are really the only ones you need, but despite that, we usually write down a special form of this. Do you know what it is? Do you remember the half angles and double angle formula? How do I get the double angle formula from these expressions? I'm trying to help you guys think mathematically. So you need a formula. Suppose I give you these expressions, and I say, please give me an expression for decomposing, for taking an angle, theta, and breaking it up into its half parts. What happens if I make B A? What is this an expression for? All right. Let A equal B equal theta. What do we have an expression for now? Well, this means that we have cos theta plus theta is cos 2 theta is equal to, right, and if I put theta and theta here, this becomes cos squared theta. This becomes sine squared theta. You get cos squared theta minus sine squared theta. Is that, you recognize this guy? Double angle formula? All right. We also get sine of 2 theta is equal to, what do we get now? We get sine theta cos theta, sine theta cos theta. So this is 2 sine theta cos theta. Oh, it's the worst. Okay, so I'm going to give you an exercise. And this is your exercise. So here's the most general form, and this is an exercise because you're going to be tested on this, right? So I want you to get some experience. This is one of your learning objectives for today. Okay, so here's the general form of a sine curve. This is for A, B, C, D, all real numbers. Okay, so you have a curve here, sine. You have a bunch of knobs. The A knob, the B knob, the C knob, the D knob. I want you to start with A equals 1, B equals 2 pi, C equals 0, D equals 0. Change them and find out what they do. Okay? You can easily look this up online, but you'll remember it better if you learn these knobs from experience. Right? Experience is better than memorization. And so go into Desmos and just like start with the sine curve and start adding, well, start changing these values. Right? So these values are set up so that what you start with is the sine curve, the basic sine curve. Right? So there's stuff that's obvious here. If I add D, this is obviously going to shift it up and down. This seems to be like a compression or expansion, but find the rest of them. I think this should also shift it left and right. So I gave you 2 of them already. So do the rest. Okay, your next exercise. Find a function that crosses the x-axis at every integer. First you have to figure out what this means, but after that it shouldn't be too difficult. Exercise. Solve x minus 2 equals 10, both using algebra and geometry. By algebra, I mean manipulate this equation somehow. By geometry, I mean plot it and then confirm that you're getting both correct. Oh, the worst. Okay, now an extremely short lecture about exponential functions. Really, here it is. 1 page. Just hang out with me. We'll do 1 board, then I'll give you a break, and then we'll do some work. Exponential function. All right, class canceled. Exponential. Exponential function. Okay, so these exponential functions are important for modeling growth. And probability. Here's the definition. definition of exponential function. This is a function that looks like this. It is f of x is equal to k times a to the power of x for k and a some real numbers. There's an important number. Before that, let's recall some of the rules. What is ax times ay? A is x plus 1. Okay, backwards working. How do I get a to the power of x times y? What do I put left here? Indeed. A to the power of x, all of this to the power of y. What about ax plus ay? Yes, sir? You don't got one. So don't use one. Don't invent one to simplify it. The best you can do maybe is you can pull out an a if you want. Like these a's are similar. So you could always pull one out and reduce them, but there's no, you can't combine these. You know if I divide that this just changes everything. So I don't really like doing multiplication and division, because multiplication and division are the same operations. So maybe I should just define how that's the case. Okay, so this rule actually implies that if I do ax divided by ay, this is actually the multiplication of ax times a to the minus y, and then we just use the same rule. And so this is not a new rule. It's just a combination of like older rules that give you that. Okay, there's a very special base called the base of the natural logarithm. Now, I can't tell you why this is special yet, because I need to tell you what the natural logarithm is. And that I can't tell you what the natural I can't tell you why the natural logarithm is important until you learn what an integral is. So for the time being, we're going to take all of this for granted. Then when we learn integration, I'll show you how we get this. But it's a special number e, and you can put it to, so I guess this is going to be e to the power of 1. Does anyone know what it is? So it is true that this is approximately equal to 2.7. But that's not what I find interesting. What I find interesting is this number is actually this. 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4, and so on. That's what this number is this. And I'll show you why later. Or there's lots of cool stuff like this. Okay, so we have a natural base e. So you can just put e in for that, and you can, I don't know, do stuff with it. So here's a question for you to do at home. Find an exponential function that passes through 3, 8. Okay. And then our final thought for today probability of flipping k many heads in a row? All right, so think about this one. So what's the probability? And this is sort of not really supposed to be in the course. So whenever I mention probability, except when we're doing an explicit application of integration, you don't have to know it. If I can only teach you stuff that you have to know and give back to me, it's going to be very boring. Right, so occasionally I just want to show you something interesting if you'll allow it. So what's the probability of flipping heads on a coin? Once. One and two, right? We flip a coin, 1 and 2. So if I flip a coin once, there are 2 outcomes. One of them is heads, one of them is tails. So half of those outcomes is the one I want, so it's a 1 in 2 probability of getting the outcome I want. If I flip the coin twice, what's the chances that I flipped a head and then another head? 1 in. So that's the same question. So if I flip a coin twice, how many outcomes are there going to be? Head, 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 tail, tail, head, tail, tail. There are 4 outcomes if I flip a coin twice. One of them is the head, head outcome. So it's a 1 in 4 chance of flipping heads twice. If I flip a coin 3 times, there are 8 outcomes. Right? One of those outcomes is the head, head, head. There's a 1 in 8 chance of flipping 3 heads in a row. So if I want to flip k heads in a row, what's the outcome? 1 over k. No. But you're in the right track. At least you've pulled k into the system. Yeah. Nope. Nope. Wait. K, no, that was close though. Yes, miss. 1 over 2 to the k. Right? Does it work? So I said k is 1. What's the outcome I should get? Flipping a coin once. 1 and 2. So is k 1? Give me 1 and 2. Yes. Yes. Answer with certainty. If I flip the coin twice, I should get 1 and 4 is the outcome. Yeah? 3, 1 and 8, 4, 1 and 16. Why did I tell you this? Why is this now at like the end of the section on exponential functions? Huh? It's not a trick. This is not a trick. What kind of function is this? Oh my God! You need exponential functions for modeling probability, even in this most basic case. Okay, so these things are naturally applicable in the real world. So I just didn't invent exponential functions. In biology, we usually show you growth, exponential growth in bacteria. Chemistry needs half-life, that's also exponential growth. Probability is, I think, the most interesting out of all of them. Right? So you need to be able to do stuff like this. Any questions? Okay, so that's going to conclude today's lecture part. I'm going to take a little break, come back, and we're going to do some worksheets for the remaining time. Let's everyone cross their oh, it's still recording.